Okay, so we'll go ahead and get started. That way we have enough time to get through everything. So hello everyone and welcome to the Academy for Eating Disorders webinar entitled Conducting Network Analysis in R with Dr. Cheri Levinson and Ms. Irina Vanzhula. My name is Kathryn Coniglio and I'll be your moderator today. Within the AED, I serve as the co-chair of the Early Career SIG along with Dr. Annie Haynos. This webinar is the second of two webinars that the Early Career SIG has sponsored this year, geared specifically towards our early career members of the Academy. The first was back in October with Dr. Laura Berner, in which she delivered part 2 of our grant writing webinar series. If you missed it, the recording is in the Early Career SIG library at aedweb.org. Also with us today is Ronald Fan, who is AED's membership manager. If you have any questions or concerns about this webinar, please feel free to reach out to Don Gannon at the AED headquarters via email at dgannon@aedweb.org. Just a couple of housekeeping items before we get started. All participants are muted except for the speakers and me. The webinar is scheduled for 60 minutes and it is being recorded, so it'll be posted in the AED website within the Early Career SIG library shortly after it ends, if you want to watch it again or download at your convenience. So as I mentioned, today's webinar is called Conducting Network Analysis in R. Statistical training in R is a topic that has been long requested by our members, so we're excited to offer some training in this area, especially from two people in the field who have become expert in this methodology. So in just a few minutes, Dr. Levinson and Ms. Vanzhula will begin their presentation, after which they'll answer some questions from the audience. Please feel free to submit your questions to the speakers during the presentation using the Q&A text box down in the bottom middle of your screen. And then when the time comes, I'll read them to the speakers. We'll do our best to get to your questions, though we may not have quite as much time as in webinars past. We'll try our best. So before we get started, Dr. Levinson and Ms. Vanzhula, let's just check your volume quickly. If you could just unmute yourself and say a few words, and if a couple of the participants can just let me know if you hear them by sending a message in the Q&A box that I just mentioned. So.
Hey everyone, this is Cheri Levinson and I'm glad to be here today.
Great, thanks.
Hi everyone, this is Irina Vanzhula and I'm excited to get us started.
Great, wonderful. And thanks for the attendees who let us know that the volume level is good. So just by way of introduction, our first speaker, Dr. Levinson, is assistant professor at the University of Louisville and the director of the Eating Anxiety Treatment Lab. Her research focuses on understanding and treating comorbid eating and anxiety disorders using tools like network analysis to personalize eating disorder treatment. Our second presenter is her advanced graduate student, Ms. Irina Vanzhula, who recently matched at the University of Chicago for her internship. Ms. Vanzhula's research focuses on improving eating disorder treatment outcomes by applying mindfulness and acceptance-based approaches to the treatment of eating disorders. She's also received intensive training in network analysis from the Psychological Networks Amsterdam Summer School and will be taking you through a demonstration of running a network analysis in R during the second half of the webinar. So with that, I'll turn it over to Dr. Levinson.
Hi everyone, glad to be here today. So we can go ahead and get started. So just briefly, today we are going to just give an overview of network theory and how to understand network models. And then Irina is actually going to talk us through a cross-sectional network model in R. We did decide to focus on cross-sectional networks just because they are the models that are being most used right now. But then at the end, we're going to talk a little bit about other applications of network analysis, so things like individual network models. And then we'll also end with some resources. Okay, so what is network analysis? So it's an alternative to latent variable theory. So for those of you who are familiar with latent variable theory, the idea behind this type of modeling technique is that there's an underlying latent variable that then produces symptoms. So if you're looking at this model here, we might think that depression is actually the cause of all of these symptoms that then go along with depression. Network theory is an alternative to this, and instead of suggesting that psychiatric illnesses are caused by an underlying latent variable, they instead suggest that symptoms are dynamical symptoms that cause psychiatric illness. So if we're looking at this example here, I think this is a pretty intuitive way to think about it. You might think about somebody who's having trouble sleeping, which then leads to fatigue, which then leads to having very low energy, and then that leads to low mood. And there can be reciprocal relations between and among all of these different symptoms. So why are we so excited about network analysis, and why have we been using it so much? Because we're able to actually look at these direct relationships between symptoms of a disorder. And on top of that, we're also able to take into account the unique relationships between symptoms. And that leads us to targeted treatment. So for instance, if we know that fatigue is leading to lack of energy, which is then leading to low mood, we can target that fatigue, and then theoretically that should impact all of the other symptoms that are being contributed to from the other symptoms of the disorder. And this can also lead to more refined theories that can really help us understand how symptoms of a disorder relate to each other. So what sorts of questions can network analysis answer? One of these questions is, what are the most important symptoms in a network or disorder? So if you're thinking about eating disorders, what are these kind of core driving symptoms that make an eating disorder keep going? We can also test how symptoms between two disorders are related. And this is especially important in eating disorders because eating disorders are so highly comorbid with other disorders. So we can actually use network analysis to say, well, how does symptoms of an eating disorder lead to symptoms of PTSD or symptoms of OCD, and what are these direct pathways? We can also start to understand how symptoms are uniquely related to one another while accounting for all of the other symptoms in the model, which leads again into these clinical implications, because we can better understand how symptoms of disorder are driving each other, and then how we can use that information to then intervene on those symptoms in a way that disrupts how symptoms are interacting with each other. Okay, so what I like to talk about is how network analysis maps onto existing theories, because I think it really nicely maps onto theory, especially in the eating disorder field. So as I'm sure everyone knows, the primary theory of how eating disorder operates is cognitive behavior theory. And most clinicians are really familiar with this theory, and they're already thinking about eating disorders as dynamical systems among cognitive, behavioral, and affective pathology. Okay. So how do we conceptualize eating disorders? So we think about people with eating disorders holding these core beliefs for themselves that then contribute to thoughts, behaviors, and affect, right? So what would this look like when we're thinking about network analysis? So CBTE theory suggests that overvaluation of weight and shape is really this core factor that drives eating disorders. So in the middle of our model, we have this overvaluation of weight and shape, which then leads to thoughts like, I can't eat this, which leads to behaviors such as restriction, as well as feeling anxious. So if we're talking about this in a network framework, we would call overvaluation of weight and shape a central symptom, and we would call the pathways between the cognitive, behavioral, and affective pathology illness pathways. So is this really changing the way we think about eating disorders? I don't really think so. I think we'd argue that we've always thought about eating disorders this way, that we've always thought about how symptoms interact with each other, and that this is what clinicians are doing on a daily basis. They're thinking about how restriction is leading to increased pathological thoughts, which is leading to confirmation of this overvaluation of weight and shape, etc. But now we have methods that we can actually use to model these symptoms and pathways. Okay, so today we're going to focus on cross-sectional networks. So how do symptoms dynamically relate to other symptoms? But it's important to remember that this is cross-sectional data. So we're just taking a snapshot in time and looking at how we're conceptualizing eating disorders using cross-sectional data and how the symptoms relate to each other. However, there are many other applications, though, with longitudinal data. And the other really important thing to think about is that network theory hypothesizes that central symptoms are really driving the maximum number of other symptoms. So what does this mean? This means that if we can identify what the central symptoms are, we should use those symptoms as intervention points, because if we can disrupt the central symptoms, if we can minimize them, that means that the other relations in the network should also start to weaken. And eating disorders are particularly well suited for network analyses because of such the close fit between the CBT model, and because they're really these disorders of symptoms that we can measure precisely and accurately and put into these models. Okay, so let's talk about how to understand network models. So this is an example of a network model, a partial network model. And what we have here are symptoms or nodes. So we have fear of weight gain, feeling fat, feeling guilty, wanting to have a flat stomach, binge eating, etc. So when you see a circle like this, we're talking about nodes or symptoms. When you're looking at these edges here, these are associations or edges or what we would call symptom pathways. So if you see a blue or a green edge, that means there's a positive relation between the symptom. And if you see a red edge, there's a negative relation between the symptom. Thicker edges are larger partial correlations, and less thicker edges are weaker relations. So there's different types of network models. There's association networks, which is basically just thinking about having a zero-order correlation matrix of symptoms. Partial correlation networks are networks that are partial correlations, so they're accounting for all relations among the other symptoms that are in the model. And regularized partial correlations are then shrinking relations among symptoms that are spurious. So I'm not going to talk much about association networks, because primarily when you're looking at the literature, or if you're wanting to do some of these network analyses, you should be focusing on partial correlations, or actually ideally Glasso, or these regularized partial correlations. So here we have a partial correlation, and here we have a regularized partial correlation, or what we call Glasso networks. You have the option to use polychoric or Spearman correlations, and that's going to depend on your data and what you're going to end up getting the best stability for. And we're going to talk about that in a bit as well. Okay, so another important point is that you cannot interpret networks visually. So when the field started, there actually were not empirical ways to quantify what was going on with these networks. So we were running these networks and we were just looking visually at what is going on with the network. But we know now that that you don't actually want to be just looking at the network and saying, well, visually this looks this way, right? Because the way that the packages are set up, you may run the same analysis and have a different visual representation just because of the time that you've run the network. Okay, so since we don't want to use visual, what do we use? We use what are called centrality indices. And centrality indices basically boil down to what are the most important symptoms. So again, going back to network theory and what I was talking about before, these are the symptoms that really are hypothesized to maintain pathology and theoretically should be a target for intervention. And the two centrality indices that we really want to focus on are strength and expected influence. And this is because there's been a lot of research that has shown that these are the most stable indices of centrality. So you may see in older research indices such as betweenness and openness being reported. But the more research that has come out, we know now that we really want to focus on strength and expected influence. And strength is the sum of the absolute edge weights between a focal node and all other nodes to which it is connected in the network. Expected influence is very similar, except it's accounting for negative edges. So if you have a network that has a lot of negative edges in it, you're going to want to use expected influence. This is how you calculate centrality, and I won't go into great depth on that. Just to show you, the main point is that you're looking at the different partial correlations between the different pathways. So how do you understand centrality graphs? So what you see here are the symptoms on the left, and what you're looking for are the ones with the highest peaks. So you see the green dot there, that's the highest centrality item, meaning it's the most important item in the network. So I talked about comorbidity and how that's a really important question that we can get at with network analysis. So how do we do that? So we actually have quantifiable ways now to look at bridge symptoms between different disorders. So the example that we have up here is a network that we've done where we looked at eating disorder symptoms, and we looked at PTSD symptoms. And what you actually see here are bridge symptoms between binge eating and irritability. And so again, this is a way to actually test how are symptoms of one disorder spreading to another disorder. So which symptom in one cluster, so for example, eating disorder symptoms, is most strongly connected to all symptoms in a different cluster? And Irina is going to show you exactly how to do that, and in the same way that there are centrality indices for overall important symptoms, you can quantify bridge symptoms. So another thing that you can do with network analysis is to compare between samples. And you can think about this if anybody's familiar with structural equation modeling and thinking about invariance tests. So if you're testing if one group's structure and their latent model is different from their structure, from a different group structure in the same model. This is the same thing that we're doing with a network comparison test, except we're comparing our networks of two different groups the same. So, and there's three different ways that we look at this. So the first is network structure and variance. So, and this is asking, is the way that nodes within the network are connected differ across samples? So are the connections different? We can also look at specific edge invariance. So are edges between two specific symptoms different between the two networks? And oftentimes you will find that there are differences just because there are so many different edges. And you can actually look at what the percent is of how many edges are different in the model. And then global strength invariance is the sum of the strengths of all edges in the network different across samples. So this can be really helpful to use, for example, if you have a clinical sample and a non-clinical sample and you want to see if the networks are the same, or if you want to compare between sexes or different ethnicities, things like that. So here's an example where we looked at a clinical network and a non-clinical network of eating disorder pathology. And in the same way, if you're thinking about comparing between any groups, this is the test that you would want to use. And this is another example from the eating disorder literature. Okay, so another really important point in network analysis is what symptoms or which items are we going to include. So it's important to remember that the network model is only going to be as strong as what you put in it. And so you may read papers and you may see that people are looking at depression and eating disorders, and they take all of the symptoms of the EDEQ and all of the symptoms of the BDI2 and they put it into their model. And that's really kind of been the thing that people have done. And that's really been what people have done in the past. But now we're starting to think more about being really careful about what we put into our models. So thinking about how we can actually think theoretically about what should go into a model, and using theory to really guide what we're putting into our models. And Irina is going to talk more about this as well. Okay. So like I just mentioned, you can use theory. There's also statistical ways to, there's a package called Goldbricker where you can actually decide, you can use that to empirically decide if you have items that are overlapping, and then you remove those from the model. So what we've been doing most recently is using theory as well as statistics to, as well as using Goldbricker to decide what items should go into our model. So again, when you're thinking about, well, I want to look at this network of self-esteem and eating disorders, you want to think really carefully about what your symptoms that you should select should be to go into your model, because it's going to completely change based on what you put into it. Okay. So now I'm going to let Irina go ahead and take over, and she's going to talk a little bit more about some other assumptions and then actually walk you through how to run these things in R.
All right, I'm going to go ahead and share my screen. All right, so in terms of sample size, the sample size really depends on the number of items that you want to include in your network. A general rule is that you want 3 participants per parameter. So for example, if you have 23 items, that means you need about 750 participants. However, that number can be lower if your network is stable. That's why it's really important to run stability. So I've seen networks with as little as about 150 participants, but not less than that. In terms of assumptions, because network analysis is so new to the literature, there aren't really official assumptions that are there for it. And a couple of things that are important. So one issue that you might come across is multicollinearity, because all the items are so similar to each other a lot of the times. And this kind of goes back to the, when you're selecting items, it's really important that they're meant to be distinct symptoms that are not measuring the exact same thing. So for example, here you have sad in blue, these depression items that might be measuring the same thing. Similar in some of the eating disorder questionnaires, judging yourself based on shape and judging yourself based on weight are very highly correlated, about 0.9, so they are kind of also really similar. Skewed data, again, like with any other model, can present an issue and bias your results. As far as missing data, if you include missing data in your analysis, it will be excluded list-wise during the analysis. You can also impute missing data if you choose to do so. So as far as network stability, so I mentioned network stability is really important. It's a test of whether or not you can actually interpret your network, and you should be proceeding with further analyses. So essentially it measures the accuracy of your network model. You can think of it as model fit in SEM. So if you have model with poor fit, you're not going to want to interpret that model. And you should, you will always going to report fit in your manuscript. So you should always be reporting stability analysis as well. So the way that stability is tested, it's bootstrapping test that creates confidence intervals and drops cases from data set and estimates correlation between parameters between new and original data set. And the stability coefficients are actually reflect the maximum proportion of cases that can be dropped, such as the correlation between original centrality indices in the reduced sample is at least 0.7. So you want your coefficient to be at least 0.2 and ideally above 0.5. So now I'm going to move into data analysis demonstration, and I'm going to be switching back and forth between slides and my R screen, because I'm going to use slides to show you the code and explain what things are in the code, but I'm also want to show you what it looks like when you actually run it in R. So we're going to start with a demonstration of network estimation and stability. So first, to run the analysis, you're going to need to download R and RStudio. Those are 2 separate softwares. And RStudio is an interface that allows you to utilize existing packages. As far as your data prep, you want to name your variables. So you want to keep the variables in your data set and name them whatever you would like. The data set should be saved as CSV, and you want to code all missing data as NA if you have missing data. So this is what my data set looks like. It has variable names at the top, and I actually named them some meaningful names. I have my missing data here as well. So I'm going to orient you to R real quick. So in R, this is our studio, and you have 4 different screens. On the top left, this is your code. On the bottom left, this is your console where all the code that you run is going to appear, and it would also print different results that you request. On the top right, you have your environment, which is going to show all of the different objects. So your data set that you upload or new data sets that you create. And on the bottom right, you're going to see any plots that you create are going to show up here. And this is also where you can install different packages that you might want. So R consists of, and one thing I'll say here is that you do not need to know how to code in order to do network analysis. There are pre-existing packages that are created for different analyses, and all you really need is to download that package and have a code example that then you will modify to for whatever you need to do and fit your data. So it's actually not as scary as it might seem from the beginning. So in R, you're going to have packages, and packages have functions and arguments. So for example, in this case, we have package bootnet, which we're going to use for our network analysis estimation. There are different functions. So package essentially is built to perform groups of analysis. So there are multiple different functions that you can do. So for example, one function we're going to use is called estimate network. And there are also arguments, which are different things that you can select to specify how you want that function to perform or how you want those analyses to run. And then there are also objects. And this left pointing arrow symbol is what we use to assign object and name in R. So I created this little demonstration here. These are not real functions in R, but this kind of helps us visualize this a little bit. So most code in the packages we work with will follow this basic example. You have your function, and then you have parentheses, and then you're going to have an object that you're performing this function on. And then after comma, you're going to have details of how this function will work. And I color coded this for ease of use. So for example, we're going to upload object, which is a function, and we're going to upload an apple. And then, so now we have this object apple. So now we're going to use a function cut, and we're doing it with object apple. And then after comma, we have different arguments for how specifically we want it cut. So we're specifying that we want 4 pieces and we want remove the seeds. Then we can assign this new object that we just created a different name. So we use this arrow to assign the object. So now it's named cut apple. And we use this exact same code. And then we can use the function display on this object cut apple to actually get the image. So this is the basic structure that all the code is going to work. So packages that we will be using for these analyses are bootnet, which you'll need for all of your basic network analyses. And then you're going to have QGraph for visualization of networks. Network tools we will use for bridge symptoms and Goldbreaker, and it has a lot of other uses. And network comparison tests to do network comparison test. You can find documentation for all of these packages online at this link, and it will have a very long PDF telling you every possible function it has and every possible argument you can use. All right, so our current sample is 823 individuals with eating disorder diagnosis. And so now I'm gonna move into showing you code. So like I said, I'm gonna show it on this screen with explanation of what is what, and then I'm gonna switch to R to actually show you how to run it. So this these green words are essentially notes in R. This is not code, and if you put this pound sign before them, the R will know that this is not code, that this is just the notes that you create. So first we are going to load the packages using the library function, and then we're going to load our data. In this case, we're going to assign our data, object name Irina's data, and then we're going to specify the directory where on your computer that data is. And then we're going to check the data if you'd like to by using this summary function. So I'm going to switch back to my R screen. And I'm going to load the packages. So you see how it showed code over here, what I'm doing. Then I'm going to load my data. And you see that in this environment on the top right corner, you have now this object is created here, 23 variables of 835 observations. And then if we want to get a summary, it will show up down here. So it's going to have your minimum, maximum quartiles and number of missing data. All right. So next thing you can do is you can assign names to your variables and assign it to object my names. You can either choose to do this here or just include these names in your data file. You can do either or. And this is the function that we're going to use to estimate our network. So we're going to assign this network object my network, and we're going to use function estimate network. We're going to use Irina's data that we've just uploaded, and we're going to use this estimator epiglasso, which is basically means that we're estimated regularized network glasso that you've seen used probably in majority of the, at least ecological literature and probably the rest. So as Cheri mentioned, different correlation methods. If you don't specify correlation method, it's going to most of the time use polychord correlation. There are some circumstances in which you might want to use spearmint, and so I've included code here for what arguments to pick if you want to use spearmint here. And then this is a code for plotting your network. So we're going to use the function plot. We're going to use object my network that we just created in the previous slide. And there are all of these different arguments that you can select to help you design your network and make it look however you want. So layouts, Spring is the most typical layout that you see. You can select node size, different colors. We're specifying names here for our variable. So you can, if you go to the QGraph package documentation, you're going to see a lot more, just numerous arguments for make your network look in whatever way that you want. So switching back to R, I'm going to go ahead and assign those names. So you see every time I create an object, it shows up in the right, in the environment here. Then I'm going to go ahead and estimate network, and I'm going to use the default function. You will see this warning message here a lot of the times that the network is dense. This happens majority of the time, especially if you use the items that overlap quite a bit. But this is the case where you might want to use spearmint. And so to plot the network, we use this code and your plot appears over here. This moment is usually very exciting when you see the network. Okay, so if you want to get this image saved to use like in a manuscript, for example, what you can actually do is you can save it as PDF. So first you set the directory for where you want it saved, and then you name your PDF, use the exact same code, but we're just going to assign it object my plot, and then this dev off function tells R to stop writing PDF. And so if you run this, this will actually save this network image as PDF in your files. To create centrality plot, we're going to use centrality plot function and use object my plot. And all of these, I have them saved as PDFs. You can create, this will create strength centrality, and this will create one for expected influence, whichever one you want to use in your analysis. And then to get centrality values for every node or every symptom in your network, you're going to use centrality table function. And this write CSV function will write that table as a CSV file. So it will save all of those. So before we go to stability, I will go ahead and run this code here. So I'm setting my directory. Now I'm saving this as PDF. And I'm going to save these as PDF. If I just run, if you save it as PDF, it doesn't show up image here, but I can run it. It will show up like that. And we will go ahead and save this. You can also get partial correlation matrix to get partial correlations for how each node is associated with the other node. So we will save that too. All right, so next thing I'm going to show you is stability. So to estimate stability, we're going to use function bootnet, and we're just going to assign it name B1. We're going to use my network as an object. You want to use at least 1,000 boots. This is essentially the better your accuracy is. And cores means how many computer cores you want to use to run the analysis. This analysis takes some time. It can take up to an hour depending on your sample size. And so if you have a really powerful computer, you can change this to 10 cores or 12 cores. If you just have a regular laptop, don't use more than 4. It might freeze your computer. And then you select which statistics you want to bootstrap. And there are 2 types of bootstrapping. There's case and non-parametric. So you want to run both. Because the analysis takes so long, it might be useful to save these files in case you want to just do the analysis again in the future. And this code you will use here to load these bootstrap files in the future. And then all of this code here will actually show you how to compute all of the different centrality metrics. So you can compute stability coefficients and different stability graphs. Okay, so I'm not going to actually run this analysis because I said it takes a while. I'm going to load the data. And I'm going to compute stability coefficients. So you can see that they show up down here. And all those are your coefficients that you need. And I'm not going to run the rest because this is just saving it all to PDF. So next thing I'll show you is how to interpret the results that we got. So first, first thing you want to look at is stability, because if your network is not stable, then you really don't go any further because we don't want to interpret a network that is not stable. So there's stability of edge weights and stability of your centrality indices. So is our network stable? So this is what an edge stability graph looks like. And we used to be interpreting the graph, but now all you really need is the stability coefficient, which is in our case is 0.75, which is excellent. This is the strength centrality stability graph. Our coefficient is 0.59, which is also very good. This is our network that we've created. And so here's centrality. So Cheri showed us how to interpret and read centrality. So essentially this is standardized. And you can look at what are kind of visually just see what are the symptoms with the highest centrality. But then what you would really need to do is look at your centrality table to find the actual standardized centrality estimates to really determine, not just visually, what are the symptoms with the highest numbers. So in our network specifically, these are the 3 symptoms that emerged as most central with their centrality values. Okay, so one other important thing is just because a symptom is more central does not mean that it's substantially more central. So in the same way that you're comparing 2 means, and if one mean is higher than another, doesn't mean that it's significantly higher, and that's what we do t-test for. So in the same way, just because one node is significantly higher than the other doesn't mean it's significantly higher. It might just be by chance or error. So one thing that we ran here and was in our code is centrality difference test. And it gives you this graph. So black squares indicate significance and gray squares indicate it's not significant. So for the 2 symptoms that we were looking at here, we can see that the square is gray means that they're not significant from each other. And you can do the same analysis for edge for edges. So here we can see is this edge here, is it significantly weaker than this edge here, as it visually appears to be. And you can do the same exact test for edge difference. And this is an example of that. All right, so next thing I'm going to show you is bridge symptoms and how to estimate bridge. For the sake of time, I'm not going to be switching back and forth anymore because this is a pretty simple code. So I'll just explain the code on the slides. So as you remember, for bridge symptoms, we want to identify what is one symptom in one cluster that's most strongly connected to all of the symptoms in another cluster or community. So in this case, we have a comorbidity network of PTSD symptoms in orange and eating disorder symptoms in green. And for example, we want to know which one PTSD symptom is most strongly connected to all of the eating disorder symptoms. So you will use the same code to upload your data and assign your node names. And you will use very similar code that we've already used to estimate and plot your network. The only difference here is that we're going to assign this my groups. So we're going to specify which symptoms belong to the eating disorder community and which symptoms belong to PTSD community. So R knows how to designate those communities. So here, symptoms 1 through 25 are eating disorder and 26 through 42 are PTSD. So we're going to estimate our network and plot, and then we'll construct a partial correlation matrix so we can actually identify partial correlations for those edges. And here is the code for estimating bridge symptoms. So we're going to use function bridge and object myplot that we've created on a previous slide. And one thing that you do here is you specify community. So there are a total of 42 items in this network altogether. So each one of the 42 items will need to have a number assigned to it. So all the eating disorder items here are 1s, and all the PTSD items here are 2s. And if you have 3 communities, which you can have, then you will assign those 3s and so on. And you specify which communities, excuse me, you want to use. Here we use all, but for example, if you have 3 communities and you really want to find bridges between communities 1 and 3, you can specify that here. And I showed you an example of what that would look like. So when you run this code in R, it will actually print your bridge strength values in a console. So it will look like this. So these would be the values that you want to report. And what you do, so then the next thing that we want to do is we want to plot your bridge centrality. So you would use this code to create my bridge object. And then we're going to plot this object. We're going to plot my bridge, and we're going to plot bridge strength, and then we can also plot bridge expected influence here. Right? And then you can actually also, and you should, estimate stability of your bridge symptoms. And this, I'm not going to go over detail through this code. This is the same code as the stability we estimated for our initial network. You just include different statistics such as bridge strength and bridge expected influence, and you're going to need to use communities arguments to specify your 2 communities. Okay, so interpreting bridge results. So as with strength, stability, regular centrality, what you want to do is you want to identify symptoms with the highest bridge centrality. And then you want to use partial correlation matrix to identify which symptom in the other community it is most strongly connected to. And then you want to repeat that for each symptoms with the highest centrality. So for example, the symptoms with the highest bridge centrality in this example is difficulty concentrating because of worrying about eating. So what we do is we use, and this doesn't exactly match, this is just kind of for visualization. Then you want to open up your age matrix, and you want to find out the symptom, difficulty concentrating, which PTSD symptom it's most strongly connected to. And in this case, it is memory problems. and I included partial correlation here. So this food concentration difficulties is our symptom with the highest bridge centrality. And this is the PTSD symptom it's most strongly connected to. And then edge or partial correlation between them can be conceptualized as sort of a bridge pathway. Okay, in the last few minutes, I'm going to show you how to do a network comparison test. So if you remember from what Cheri told us, NCT can help us answer 3 different questions. First, are the edges between the same nodes different in the 2 networks? So here we have a clinical network and a non-clinical network. So for example, we want to see, is the edge between binge and purge in clinical network stronger or weaker than the edge in non-clinical network? And then, so this is an overall invariance test. And then if there is a difference, overall difference, then you can test which specific edges are different. And the third question you can answer is, are the sums of all edges, or what's also referred to as global strength, different between the networks? So going back to code for this, you're going to want to load 2 different data files. NCT does not like missing data, so you can use this code to omit missing data, or you can impute it. And you're going to want to estimate both networks, same way we did. And here's the code for NCT. So you're going to use NCT function. And for objects, you're going to have 2 objects this time because you're comparing 2 different networks. So we're going to use my network 1 and my network 2. And for iterations, usually you want to use at least 1,000. Again, I've seen people use 100. The more iterations, the more accurate it is. And for the first time you run it, I recommend to put test edges as false, because if your edge invariance test is not significant, there's really no point in testing individual edges. And this test is also pretty time consuming. And if you test all the edges, it's going to take about 10 times longer. Another thing here that I'll mention is that this is actually a fairly new function to be able to use your network object for NCT. What we used to do is just use the data object. So you would put Irina data 1 and Irina data 2 here. And this new function is pretty cool because when you run the network, you can specify a lot of different things. So for example, if you want to use Spearman correlation, you can specify that here. And then your NCT will also use Spearman correlation. So it's a way to save all of the functions that you selected. And then you're going to use summary function to get the results of your NCT test. And again, this will be printed in your console. So it's going to look like this. So first, you're going to get results of your network invariance test. And you're going to get your test statistic. And you, as with any analysis, you're going to look at your p-value. So in this case, it's not significant. So if it's not significant, that there's really no reason to test individual edges. And if you did test individual edges, that would print another really long result. And then our global strength invariant test, we're going to have this lists global strength for each network. So it's 12.77 and 12.91, which is very similar. So not surprisingly, the test is not significant. So that means that there's really no difference in global strength between our networks. And this example right here is what I've included as an example of a write-up that you can use. You can also look at any of our papers for examples on how to write that up. And so I know I went through this pretty quickly. I'm going to have Cheri go through the rest of the material on what else you can do. But I am happy, and both of us are happy to answer any questions about the code. I know I kind of packed a lot in here and went through it pretty quickly. So if you have any specific code questions, feel free to email me. All right, and I'll go ahead and turn it over to Cheri.
Okay. So, okay, so I'm just going to talk a little bit about other things that you can do with network analysis, because we've really just been focused on cross-sectional data. But so in addition to looking at cross-sectional data with continuous variables, you can use MGM and look at dichotomous and count variables. So you're making a cross-sectional network, but without that continuous like scales. So an example might be if you say have a large epidemiological data set that you have yes/no variables for, and you want to look at relations between that. You can also use MLVAR, which is longitudinal group level modeling. So this basically means that you can look across time, across groups, and test how symptoms at time 1 are predicting at the next time point. Graphical VAR is very similar, except instead of modeling at the group level, you can actually model individual level data. So you can model for one person what their symptoms look like across time. And then a really new package is psychometrics. And you can, in this package, actually do a combination of latent network models, as well as you can actually test model fit for networks, which is really important because we didn't used to have ways to actually evaluate how well the model fit the data. Okay, so what other things can you do? So one thing that we've been increasingly interested in is really testing this idea of if central symptoms are actually important, right? Because do we actually want to use these as intervention targets or not? So there's been several research studies coming out recently that has actually started to look at taking the central symptoms from the model and then testing if that predicts later outcomes. And we've been finding that yes, central symptoms do actually predict outcomes, which is providing evidence that these may actually be really important treatment targets. So this is an example of a latent network model, as I mentioned. So what you can do with these models is actually, if what you're trying to model is something that you think is a combination of latent variable models and network models together. This is an example of a temporal group network. So again, what that is looking at across time, across people, how these symptoms are relating to each other. And importantly, to look at this type of question, you need to have intensive longitudinal data. So usually that would look like having ecological momentary assessment, usually across like at least 2 weeks. So ideally, you want to have 100 measurement points. So this is an example from our data with 62 participants and 48 observations, looking how symptoms predict each other across time. And this is an example of an individual network. So this is for one individual, how their symptoms interact with each other. And of course, you can imagine how this applies to clinical intervention, because if you can model for one person what their pathology is and what their maintaining symptoms are, you can then use that data to inform that specific person's treatment. For individual networks, you get temporal and contemporaneous networks, and temporal are looking across time. So if we have an EMA lag of 4 hours, you're looking at how binge eating predicts judging oneself across 4 hours. And contemporaneous is looking at how symptoms impact each other at the same time while controlling for the longitudinal relations. So there's some other uses that I'll just end on, because network analysis, I mean, we've primarily been seen it used in these cross-sectional data sets, but there's lots and lots of flexibility with using network analysis. So you can, for example, have an experimental manipulation and then look at how that experimental manipulation then impacts other symptoms that you've collected during the manipulation. You can look at comparisons across treatment. So how are symptoms changing across treatment? You can also look at task-based measures. So for example, maybe you have a measure of fear conditioning or habit learning, and you're getting behavioral measures that you can then put into a network model. You can also look at pre-post treatment change. So you can have a network before treatment and after treatment, and use something like the NCP to test if you're seeing change in the person's network across time. And of course, there's many more uses, but those are just kind of the most important ones to touch on. So we do have resources in the slides that we'll be providing. And we are, as Irina said, always happy to answer questions or consult on things as needed.
Great, thank you so much. I think we have time for a couple questions that are coming in. Most are logistical. One question is, Irina, I think you alluded to this privately in the beginning. Someone's wondering if you'll be able to share the slides and or the R scripts with everyone.
Yes, I can. So what we'll do is we'll post the slides and I'll post the R script on our lab website, and then I will send you a link, Kathryn, and then you can distribute it to everyone else.
Great. And then someone has a question about whether within RStudio, if you have to download your network analysis package once, or if you need to do that every time. And I guess a broader question that some folks might be wondering, if you're new to R and this is sort of like learning a new language, are there, I know you quickly shared some resources at the very end there, but was there anything that you really felt like was helpful in learning R before you try and tackle a network analysis, if you're more in the beginning stages? If you could just speak to that.
Yeah, so you do download a package once, but you have to load it every time you start R. So the code that I showed you using the library function, that has to be run every time that you open RStudio, but you download it just once. In terms of learning R, there's actually, I think, a couple things in our slides for learning R, but even if you just Google, R is free and it's open source. So a lot of people put a lot of effort into making sure that it's accessible to everyone. So there's a lot of different free things on the internet that you can just watch on what R looks like and operates. But the way I kind of learned it is just, I had a very basic introduction to objects, packages, functions, and then I took someone else's code as an example, and I just kind of played around with it and modified it. So I didn't necessarily take a course in R or anything, because all you need is just an example code, and then you can kind of plug different things in and see what comes out.
Some trial and error for sure, but that's the nice thing about R. Great. So I don't see any other questions, but the Irina and Dr. Levinson's emails are down there if you have any questions that come up after the fact. And so that about wraps it up. Thank you again to our presenters. This was, I know, judging by the number of attendees, I could tell this was a topic that people have a lot of interest in. So thank you again for sharing your time. Just a reminder, you can find out more about upcoming webinars by visiting aedweb.org under the events tab. And thank you, everyone. Thanks very much, and have a good rest of your day.